Welcome, dear listener. You've found your way to Dreams of Gravity, and I'm so glad you're here. Before we begin, I want you to do something for me. If you haven't already, find a comfortable position. Maybe you're lying in bed right now, the blanket pulled up just a little, the room dimmed and quiet. Maybe you're in a chair, legs stretched out, eyes already growing heavy. Maybe you're somewhere unexpected. A couch in a quiet living room, a window seat with the glass cool against your shoulder, headphones in, the rest of the world held gently at a distance. Whatever position feels most natural to you, settle into it. Let your shoulders drop, let your jaw loosen. Let the tension in your hands dissolve like sugar in warm water. You don't have to hold anything right now. You don't have to be anywhere. You're exactly where you need to be. Take a moment to notice your body, the weight of it against the surface beneath you. The way your legs feel heavy, your arms feel loose, your chest rises and falls without any effort from you at all. Your body has been working all day, carrying you through all the small and large demands that a day places on a person. And now it gets to rest. Now it gets to simply be still. There's a particular kind of relief in that. A release that begins at the edges and moves slowly inward, like warmth spreading from a fire on a cold evening, radiating outward from its source in slow, comfortable waves, touching first your hands, and then your arms, and then the center of your chest, where something that has been held tight all day begins, finally, to loosen. Tonight, I want to take you somewhere vast, somewhere humbling and beautiful and strangely peaceful. I want to talk about something that sounds dramatic on the surface. An asteroid, a collision, a moment of cosmic consequence. But I promise you, by the time we're finished, it will feel less like a disaster story and more like a meditation on time, on scale, on the ancient and patient life of this planet we call home. Because that's the strange magic of thinking about the universe. The bigger the scale becomes, the quieter everything feels. The more you zoom out, the more the ordinary worries of an ordinary day begin to soften into something manageable, something small in the best possible sense. So breathe in slowly, hold it just for a moment, and breathe out. Let's begin. The rock begins its journey. Somewhere out beyond the orbit of Mars, in a vast and shadowy region of space called the asteroid belt, there are millions of rocks drifting. Some are no larger than a pebble, some are the size of a house, and a few, a rare few, are the size of mountains or cities or small countries. They've been out there for over 4 billion years, orbiting the sun in lazy, slow ellipses, most of them never coming close to Earth at all. They are leftovers, remnants of the early solar system, material that never quite came together to form a planet, held apart by the gravitational pull of Jupiter, that enormous gas giant standing guard in the outer solar system, like a quiet sentinel that has been at its post since the very beginning. It's worth pausing to appreciate just how long 4 billion years really is. If you compressed the entire history of the solar system into a single calendar year, so that January 1st represents the formation of the sun, and December 31st at midnight represents right now, then the asteroid belt has been exactly where it is since roughly January 5th. The first simple life on Earth doesn't appear until sometime in March. Complex multicellular life doesn't emerge until November. The dinosaurs don't appear until mid-December. Human beings, with all our art and language and civilization and science, appear in the final minutes of December 31st. Everything we have ever done, every empire that has risen and fallen, every book ever written, every song ever sung, every city ever built, all of it fits inside the last few seconds before midnight. And the asteroid belt was already ancient before any of that began. It was ancient before the first fish swam in the first ocean, before the first plant pushed a root into the first soil. That scale is difficult to hold in the mind, and I think that's okay. It's not meant to be held. It's meant to be felt, dimly, the way you feel the depth of the ocean from the surface. Not by seeing the bottom, but by sensing the vastness below you. Just let the number drift. 4 billion years, ancient beyond imagining, and the rocks still turning, still drifting, still patient, still there. Most of these rocks will drift in their ancient paths forever, undisturbed, forgotten. But every so often, across geological timescales that dwarf human history, the gravitational dance of the planets nudges one of these wanderers. A slight shift in trajectory, a slow, gentle drift inward. Jupiter's gravity, the same force that keeps most asteroids safely in the belt, occasionally acts like a billiard cue, sending a rock on a new path, one that crosses the inner solar system, one that eventually, over millions of years of gradual orbital evolution, brings it into the neighborhood of the rocky planets. Mercury, Venus, Earth, Mars. Worlds with surfaces, worlds that can be struck. It has happened before, many times. The surface of the moon, if you look at it on a clear night, tells you the story plainly. All those craters, all those ancient scars, are the record of collisions. Billions of years of cosmic rain. The moon has no weather, no erosion, no tectonic activity to heal its wounds. Every impact it has ever suffered is still visible, preserved in the grey and silver surface, like a diary written in stone. Astronomers have catalogued thousands of lunar craters, some of them hundreds of kilometers wide, relics of the early solar system's most violent period, a time called the Late Heavy Bombardment, roughly 4 billion years ago, when the inner solar system was being pummeled by debris at a rate that is almost impossible to comprehend today. Earth has been struck too, again and again, though our planet's restless geology, its volcanoes and shifting plates and wind and rain, has slowly erased most of the evidence over time. But if you know where to look, the scars are still there, deep in the rock, encoded in the layers of ancient sediment, waiting to be read by anyone patient enough to look. One of the most beautiful examples is the Barringer crater in Arizona, a bowl of rock about 1.2 kilometers wide and 170 meters deep, sitting in the flat desert landscape, like something pressed gently into the earth by an enormous thumb. It was formed roughly 50,000 years ago by an iron meteorite perhaps 50 meters across. Small by the standards of what we're discussing tonight, but large enough to leave a scar that is still perfectly preserved, still striking, still capable of producing a kind of quiet awe in anyone who stands at its rim and looks down into its silent interior. 50,000 years is nothing in geological time. In human terms, that impact happened while our ancestors were painting images on cave walls in Europe and Asia, while mammoths still walked the grasslands of Siberia. The universe was busy then, as it always is. There are other craters too. The Vredefort Dome in South Africa, roughly 2 billion years old and over 300 kilometers wide, so old and so eroded that from the ground it doesn't look like a crater at all, just a range of gently rolling hills, its origin revealed only by the microscopic shock features preserved in the ancient rock. The Sudbury Basin in Canada, 1.8 billion years old, its impact so energetic that it melted vast quantities of rock and concentrated valuable metal ores that humans now mine. The Manicouagan Reservoir in Quebec, a circular lake visible from space, filling the remnants of a crater formed 215 million years ago, so perfectly circular that it looks like a cosmic drawing compass was pressed into the Canadian wilderness and rotated. Each of these craters is a chapter in Earth's long story, a record of violence that happened, was absorbed, and was eventually transformed into something ordinary. A desert bowl, a range of hills, a lake where fish swim and birds nest, and the surface of the water reflects the sky. I find myself wondering sometimes what it would have looked like to watch one of those ancient impacts from a safe distance. From orbit, perhaps. The flash of light, the slow spreading ripple of the shockwave moving outward through the crust, the rising column of superheated dust and rock reaching up into the sky like a dark flower blooming in slow motion, rising above the atmosphere itself and spreading outward in a mushroom of glowing debris. And then the long, quiet aftermath, the cooling, the dust settling, the slow return of silence, the way life, wherever it had survived, would have gradually crept back toward the devastated zones. Tentative at first, then more boldly, filling in the silence the way plants always do, the way water always finds the lowest ground. There is something almost meditative about thinking on those timescales. The violence of the impact is real, but it is also temporary. Geological time is vast enough to absorb even the most catastrophic events and eventually smooth them into continuity. The wound heals, not quickly, not completely, but inevitably, inexorably, over the long patience of millions of years, the landscape returns to a kind of equilibrium. New species fill the emptied niches, new forests grow over the ashen soil, new rivers carve their paths through the reshaped landscape. The earth keeps moving. The earth always keeps moving. By the way, I find myself curious about something, if you don't mind me asking. Where are you watching from tonight? Which city are you in? And what time of day is it for you right now? Are you lying there in the deep quiet of midnight, or in the early hours of the morning when the world feels still and far away? Are you somewhere cold, tucked under a heavy blanket, or somewhere warm, a window cracked open to let in the night air? I love imagining all the different places people find their way to a video like this. All those different rooms, all those different beds and chairs and quiet corners of the world, each one dark and peaceful and turned just for a moment toward the stars. It's a small thing, but it makes the universe feel a little warmer somehow. It makes the distance between us feel like less. But let's continue, because the story we're exploring tonight is one of the most fascinating thought experiments in all of science. And I want to take it slowly, gently, one step at a time. A specific rock. Let's imagine a specific asteroid. Let's give it a size, say 10 kilometers across. That's roughly 6 miles in diameter. To put that in perspective, if you placed it in the center of a major city, it would cover the entire downtown core and the surrounding suburbs and stretch out into the farmland beyond. It's not a pebble. It's not even a boulder. It's a mountain, an ancient, tumbling iron and silicate mountain that has been drifting through the solar system since before the first single-celled organisms appeared on Earth. Asteroids come in several broad categories, and understanding the difference matters for understanding what an impact would involve. The most common type, called carbonaceous or C-type asteroids, are dark and primitive, composed largely of carbon-rich material and hydrated silicates, sometimes containing organic compounds and even traces of water locked in their mineral structure. These are among the oldest objects in the solar system. Their chemistry barely changed since the first days of planetary formation. Then there are the S-type or silicaceous asteroids, brighter and composed primarily of silicate minerals mixed with metallic iron and nickel. And finally, the M-type or metallic asteroids, dense, bright, composed almost entirely of iron and nickel, the remnant cores of larger bodies that formed, differentiated, and then were shattered by collisions in the early solar system, leaving their metallic interiors exposed. Our imagined 10-kilometer asteroid is somewhere between S-type and metallic, dense, irregular, cold, its surface covered in a thin layer of fine rock powder called regolith that has accumulated over billions of years of micrometeorite impacts. It tumbles slowly on its axis as it travels, catching the light of the distant sun on one face and then the other, casting long shadows across its own cratered landscape. If you were to stand on its surface, which you could, because its gravity, though tiny, would be enough to keep you anchored, you would see a landscape of grey rock and black shadow. The stars overhead utterly unblinking in the airless void. The sun, a brilliant but distant point of light, far smaller than it appears from Earth, casting a harsh and shadowless illumination across the barren terrain. This is the object that Earth scientists dread most. Not because it's the most common, smaller objects hit us far more frequently, but because objects in this size range are large enough to cause truly global consequences, yet not so large that they're easy to detect decades in advance. The very largest asteroids and dwarf planets, objects hundreds of kilometers across, are all already catalogued. We know where they are. None of them pose a threat to Earth in any foreseeable time frame. But in the 10-kilometer range, the catalogue is less complete. There may still be objects of this size in orbits that cross Earth's path, not yet discovered, not yet tracked. This is, in fact, very close to the size of the object that struck our planet approximately 66 million years ago. The impact that ended the age of the non-avian dinosaurs and reshaped the course of life on Earth entirely. Scientists call it the Chicxulub impactor, named after the crater it left buried beneath the Yucatan Peninsula in Mexico. That crater is roughly 180 kilometers wide and extends into the floor of the Gulf of Mexico. It is one of the largest confirmed impact structures on the planet, and it has been sitting quietly beneath layers of limestone ever since, patient and hidden, waiting to be found. It was found, eventually. Not by looking at the surface. The crater is invisible to casual observation, buried under millions of years of geological accumulation. But by careful study of gravitational anomalies, of unusual rock formations, of the strange circular patterns in the Yucatan's underground river systems that hint at something vast and ancient beneath. Geologists began piecing the story together in the late 1970s and early 1980s, led initially by physicist Luis Alvarez and his son Walter, a geologist, who noticed an anomalous layer of iridium in rock formations around the world that corresponded precisely to the boundary between the Cretaceous and Paleogene periods, the exact moment in geological time when the dinosaurs disappeared. Iridium is rare on Earth's surface, but common in asteroids. The only mechanism that could deposit a global layer of iridium simultaneously across the entire planet was a very large extraterrestrial impact. The Alvarez hypothesis was controversial when it was proposed. Today, it is the scientific consensus, supported by overwhelming evidence from dozens of independent lines of inquiry. Here was the smoking gun. Here was the mechanism behind one of the greatest mass extinctions in the history of life on Earth. A rock from space, 10 kilometers wide, falling from the sky on an ordinary afternoon 66 million years ago, changing everything. When we try to understand what would happen if something like that struck today, we're not doing science fiction. We're drawing on very real geological evidence, very real physics, and very real computer models that planetary scientists have built with painstaking care over decades of research. What would the sequence of events look like, second by second, hour by hour, day by day, year by year? It's a question worth sitting with quietly. Not because it should frighten you, and I truly mean that, but because understanding it more deeply gives us something remarkable. It gives us perspective. It reminds us of the extraordinary fragility and resilience of life. And somehow, in the quiet of the night, that perspective is one of the most calming things I know. Let your breathing slow down a little more. There's no rush. We have all the time in the world. The final approach. In our thought experiment, astronomers have spotted the asteroid early. Let's say 18 months before impact. That's actually a realistic detection window for a large object, given the current state of planetary defense monitoring systems. Telescopes around the world, and a few in space, are watching the skies constantly, cataloguing near-Earth objects, tracking their trajectories with extraordinary precision. Programs like NASA's Center for Near-Earth Object Studies and the European Space Agency's Planetary Defense Office exist specifically for this purpose. Quiet, patient, methodical work, done mostly in the background, mostly unreported, mostly unnoticed, until it matters. When the detection is made, there is a careful, methodical process. An initial observation is flagged. Other observatories are alerted. Independent measurements are taken from different locations on Earth and from space-based telescopes. The orbit is calculated and recalculated, refined with each new data point, the uncertainty shrinking as more observations accumulate. Scientists use a scale called the Torino scale, a 10-point system that combines the probability of impact with the estimated energy of the collision to produce a single hazard rating. For most near-Earth objects, the Torino scale reading is 0, no hazard. For our imagined asteroid, the reading climbs steadily as the orbit is refined, passing through the yellows and oranges on the scale until it reaches the red zone at the top. A certain impact, a global catastrophe. What happens next in a world with 18 months of warning is a fascinating exercise in both science and human nature. The physics are clear. The engineering options are limited. Deflection missions that could realistically be assembled and launched in 18 months would have very little time to operate before the asteroid arrives. Not enough to change its trajectory meaningfully. Nuclear standoff detonations, the most powerful tool in the theoretical planetary defense arsenal, might be able to break the asteroid into smaller pieces. but those pieces would still be on roughly the same trajectory, and a swarm of smaller impacts might, in some scenarios, be worse than a single large one. And so, the conversation shifts from prevention to preparation, from planetary defense to civil defense. Where is the impact expected to occur? If it's an ocean impact, which is statistically more likely since oceans cover roughly 70% of Earth's surface, then the concern becomes the enormous tsunamis that would radiate outward from the impact site, crossing entire ocean basins and striking coastlines thousands of kilometers away. Coastal evacuations on a scale never before attempted. If it's a land impact, the local destruction radius would be measured in hundreds of kilometers. But the global effects, the winter, the darkness, the collapse of agriculture, would be felt everywhere. 18 months sounds like a long time. In some ways, it is. It's enough time for the news to spread, for governments to convene, for scientists to model the impact parameters. It's enough time for people to have long, quiet conversations about things that matter to them, to say things they'd been meaning to say, to visit places they'd been meaning to visit, to sit with the people they love in the particular golden light of a late afternoon and simply be present. There is something strangely clarifying about that kind of deadline. Not the panic, that's understandable and human and real, but underneath the panic, for many people, a kind of simplification. The noise falls away. The things that truly matter become obvious. Food and warmth and the people you love. The smell of rain on warm pavement. The sound of a child laughing. The way the sky looks at dusk when the colors are just right, and everything feels suspended for a moment between day and night. People have written, in the thought experiments and fiction inspired by this scenario, about how the knowledge of a shared fate creates a strange kind of intimacy between strangers. The barriers that ordinarily separate us, nationality, language, wealth, politics, begin to feel less solid. We are all, in the end, on the same small island. For an object this size, with this little warning, there is no deflection. The outcome is fixed. The physics are decided. And so, the world watches. The asteroid is not visible to the naked eye until the final weeks. Then it appears as a faint, steady point of light, not twinkling the way stars do, because it's too close for that, moving too perceptibly against the background of the sky. Night by night, it grows brighter. Amateur astronomers track it obsessively. Websites update its position in real time. Children point it out to their parents from backyard gardens. In the final days, it is visible in full daylight. A hard, brilliant point of white light, moving slowly but perceptibly across the sky, resolving finally into a shape in the highest-powered telescopes. Dark grey, irregular, ancient, tumbling slowly on its axis as it falls inward through the last millions of kilometers of space between it and us. It will enter Earth's atmosphere at roughly 20 kilometers per second. That's about 72,000 kilometers per hour. At that speed, the entire thickness of the atmosphere, from the stratosphere to the surface, takes approximately 5 seconds to traverse. 5 seconds from first atmospheric contact to impact. In those 5 seconds, something extraordinary happens. Fire from above. The asteroid hits the atmosphere like a hammer hitting a wall of water. The air in front of it has no time to move aside. It compresses instantaneously. It heats. In a fraction of a second, The temperature of the compressed air in front of the asteroid's leading face reaches tens of thousands of degrees, hotter than the surface of the Sun. The front of the rock begins to ablate, to vaporize, peeling away in streams of superheated plasma, trailing light like a second sun falling from the sky. The bolide, which is what scientists call a meteor that produces a fireball, would be visible from an enormous area of the Earth's surface simultaneously. Not as a streak, but as a growing, intensifying source of light, brightening exponentially with each passing second. This is what a meteor is on a small scale. That flash of light you see on a clear summer night, that brief silver scratch across the darkness. That's a piece of rock the size of a grape, burning up in the upper atmosphere, transformed into a momentary point of brilliance, and then gone, leaving you blinking in the dark and wondering if you really saw it. Meteors are beautiful, precisely because they are brief. The universe, for one flickering second, draws a line across the sky and then erases it. Now scale that up to 10 kilometers of ancient iron and silicate rock, moving at 72,000 kilometers per hour, and the light produced is not a scratch. It's a flash bright enough to be seen from the entire day side of the Earth simultaneously. Bright enough to cast sharp shadows at noon on a cloudless day. Bright enough that people thousands of kilometers away, with their backs turned, would see the landscape in front of them suddenly illuminate as if a second sun had appeared directly overhead. A pulse of light so intense and so brief that it would leave after images burned into the visual field for minutes afterward. The sound would come much later. Sound travels at roughly 340 meters per second through air, far slower than light, far slower than the asteroid itself. People hundreds of kilometers away would see the flash and then wait in eerie silence for the sound to arrive. And when it did arrive, perhaps 15 minutes later, perhaps 30, depending on the distance, it would arrive not as a bang, but as a sustained, rolling pressure wave, a physical force powerful enough to shatter windows and knock people off their feet at distances of hundreds of kilometers from the impact site. The rock reaches the surface in those 5 seconds. It does not slow down appreciably. The atmosphere is not thick enough, not massive enough to stop something this large. It punches through and strikes the ground, or the ocean depending on where it lands, still moving at nearly its original speed, carrying with it a kinetic energy almost impossible to comprehend in human terms. What this translates into, physically, is something that challenges the ordinary imagination. The asteroid does not just hit the ground, it passes through the ground. In the first seconds after impact, it excavates a temporary transient crater hundreds of kilometers wide and tens of kilometers deep, punching through the crust of the Earth like a finger through a soap bubble. This transient cavity, initially as deep as 25 or 30 kilometers, immediately begins to collapse under its own weight, the walls sliding inward and the floor rebounding upward in a process that takes minutes but feels, in the timescales of rock, almost instantaneous. The final structure, the complex crater that remains after this collapse, is shallower and wider, with a central peak or ring formed by the rebound of the crater floor, surrounded by concentric rings of disturbed and fractured rock. Rock and soil, and, if it's an ocean impact, vast quantities of water. They are not just splashed aside. They are vaporized instantly and launched upward at speeds approaching escape velocity. Some of that material actually reaches orbit. Chunks of rock moving fast enough to escape Earth's gravity entirely enter independent orbits around the Sun, joining the asteroid belt as small new members, carrying traces of Earth's crust into interplanetary space. This is, incidentally, how material is exchanged between planets. Mars has been found to contain minerals that originated on Earth, and vice versa. The solar system is not as tidally separated as it appears. The planets have been trading material through exactly this kind of violent exchange for billions of years. Breathe slowly. You're safe here. This all happened very, very long ago. And we're simply watching from a great distance with the gentle detachment of deep time. The first minutes, in the seconds and minutes immediately following the impact, the scene is one of almost incomprehensible energy release. A shockwave spreads outward through the ground at several kilometers per second, far faster than any surface process, faster than wind, faster than sound, propagating through the solid rock of the crust as a compression wave that shatters and melts everything in its path for hundreds of kilometers in every direction. This is not a normal earthquake. The largest earthquakes ever recorded, magnitude 9 events, the kind that rearrange coastlines and trigger tsunamis, release energy in the petajoule range. The shockwave from a 10-kilometer impact releases energy many orders of magnitude greater. The ground moves not in the way it does during a typical earthquake, that familiar rolling, swaying motion, but in a sudden, violent displacement. Rock that has been solid for hundreds of millions of years is briefly behaving like liquid, flowing outward from the impact site in a ring of destruction that spreads at the speed of sound through stone. The entire planet rings like a bell. This is not a metaphor. Seismographs would record oscillations in Earth's crust for days afterward, the planet literally vibrating at its own natural frequencies, like a struck tuning fork slowly returning to stillness. Every seismograph on the planet simultaneously would go off the scale. Volcanoes that have been quiet for thousands of years are triggered simultaneously across multiple continents, their magma chambers destabilized by the global seismic shaking. The Yellowstone supervolcano, the volcanoes of the Pacific Ring of Fire, the ancient calderas of Africa and Europe, all of them responding, each in their own way, to the sudden violent ringing of the Earth. Simultaneously, at the impact site itself, something extraordinary is happening with the atmosphere directly above the point of impact. The asteroid's passage through the atmosphere has punched a temporary hole, a column of near vacuum where air has been explosively displaced. This column then collapses back on itself, sending a secondary shockwave upward that interacts with the re-entering ejector in complex and devastating ways. The fireball at the impact site reaches temperatures of tens of thousands of degrees, briefly as bright as a small star visible from space, sending thermal radiation outward in every direction. For anyone within a few hundred kilometers of the impact site, survival is not possible. The thermal pulse alone, the flash of radiant heat, would be lethal at distances approaching 1,000 kilometers, arriving at the speed of light and causing third-degree burns before the sound of the impact has even begun to travel. The overpressure wave following close behind would flatten reinforced concrete structures at distances of several hundred kilometers. The ground displacement would make normal footing impossible. In a very real sense, for a large portion of a continent, the impact itself would be the end point, swift, total, leaving nothing that requires further explanation. For people far from the impact site, on the other side of the planet, in deep valleys or underground, survival of the immediate event would be possible. But the consequences that follow would be far more pervasive and long-lasting than the initial blast. The tsunami question. If the asteroid strikes the ocean, which is statistically the most likely outcome since oceans cover roughly 70% of Earth's surface, the immediate local consequences differ somewhat from a land impact, but the global consequences are very similar. The energy release is the same. The ejecta are the same. The global firestorm and the impact winter proceed in essentially the same way. But there is an additional threat unique to ocean impacts, the tsunami. And not just any tsunami. The displacement of water from a 10-kilometer impact would generate waves of an entirely different order of magnitude from anything in recorded human history. The largest tsunamis ever observed, generated by the most powerful submarine earthquakes, produced waves of perhaps 40 or 50 meters in height as they approached coastlines. The waves generated by a 10-kilometer ocean impact would be measured not in tens of meters, but in hundreds. Perhaps more, depending on the depth of the water and the distance from the impact site. These waves would cross entire ocean basins in a matter of hours. A Pacific impact would send waves toward every coastline bordering the Pacific, the Americas on one side, Asia and Australia on the other, all of them arriving within hours of the impact, giving coastal populations limited time to evacuate, even in the best-case scenario. The waves would not look like the tsunami waves most people imagine, a single dramatic wall of water arriving suddenly. They would be felt first as a slow, deep swell, an unusual rising of the sea over many minutes, before the full energy of the wave came ashore. And when it did come ashore, it would not stop at the beach. It would continue inland for kilometers, its energy carrying it far beyond any coastline that has ever been touched by ocean water in human memory. The geological record contains evidence of ancient mega-tsunamis triggered by large impacts. Enormous sheets of marine sediment deposited hundreds of meters above sea level, far inland, in areas that should never have been touched by seawater. These deposits are found on multiple continents, silent witnesses to events so large they rewrote the local geography in a single afternoon. The hours after. In the hours following the impact, whether it strikes land or ocean, the global atmosphere begins to transform. The material launched into the upper atmosphere from the impact site, combined with the smoke and soot from fires ignited across large portions of a continent, begins to spread. The stratosphere, which ordinarily acts as a stable layer above the weather, becomes a repository for billions of tons of fine particulate matter. Wind patterns in the stratosphere carry these particles around the globe with surprising speed. Within days, the first effects of reduced sunlight would be noticeable in regions far from the impact site. Within weeks, the dimming would be significant. Within months, it would be severe. The atmosphere itself would undergo chemical changes in the aftermath of the impact. The extreme heat of the bolide's passage through the air would cause nitrogen and oxygen molecules to combine, producing nitrogen oxides, compounds that, when they eventually dissolve in rainwater, fall back to Earth as nitric acid rain. This acid rain, distributed globally, would damage plant life and acidify the surface layers of the oceans, adding another layer of stress to already struggling ecosystems. The chemical composition of the oceans themselves would shift as enormous quantities of rock vaporized from the impact site rained back down into the water, changing its pH and temperature in ways that would take centuries to fully correct. And yet, and this is the part I keep returning to, the part that I find both humbling and consoling. Earth has survived this before. Not just survived it, but gone on, after a period of darkness and loss, to produce something more extraordinary than what existed before. That is the nature of this planet. That is what the geological record, read carefully and honestly, actually says. Not that life is invulnerable, not that catastrophes are trivial, but that life, given enough time and enough darkness and enough patience, finds a way. The long winter. In the weeks and months following the impact, the most persistent and devastating consequence is not the fire or the earthquakes or the initial blast. It is the darkness. The explosion and the subsequent wildfires inject enormous quantities of dust and soot into the stratosphere, where particles can remain suspended for years without being washed out by rain. This stratospheric veil blocks sunlight. Not completely, the world doesn't go entirely dark, but enough to reduce photosynthesis dramatically across the entire planet. Enough to drop average global temperatures by 10, 20, perhaps 30 degrees Celsius over the course of months. This is called an impact winter, and it is the mechanism by which a single geological event cascades into a global extinction. The chain of consequences is elegantly terrible in its simplicity. Less sunlight reaches the surface. Photosynthesis falters. Plants die. The animals that eat plants begin to starve. The collapse propagates up through every food chain on the planet, from the microscopic phytoplankton in the oceans to the great forests on land, until the entire web of life is under simultaneous pressure from every direction at once. Imagine waking up one morning and noticing that the light seems a little less bright, and the next morning a little less again. Not dramatic, not the sudden switching off of a lamp, more like a long, slow dusk that never quite gives way to dawn. The temperatures dropping gradually, imperceptibly at first, then undeniably. The crops failing, the insects disappearing, the birds going quiet, the rivers freezing earlier than they should, the nights growing longer in a way that doesn't correspond to the season. Scientists have modeled impact winter scenarios using the same atmospheric simulation tools developed for studying nuclear winter. The hypothetical climate effect of a large-scale nuclear exchange, which would also inject vast quantities of soot into the stratosphere. These models consistently show that a 10-kilometer impact would produce temperature drops severe enough to fail agriculture globally for at least a year, and possibly for several years in the worst-case scenarios. For a modern human civilization of 8 billion people, dependent on global agricultural systems that operate with very little buffer stock, even a single year of dramatically reduced harvests would produce consequences that compound in complex and devastating ways. The oceans are particularly vulnerable over the longer term. The surface waters that support vast communities of microscopic life depend on sunlight just as much as any forest. When the light dims, the phytoplankton die. And when the phytoplankton die, everything that depends on them begins to feel the effect. Not just the fish and marine mammals, but also the ocean's capacity to absorb carbon dioxide from the atmosphere, which is partly dependent on phytoplankton growth. The disruption of ocean chemistry following a large impact is one of the longest-lasting consequences, playing out over centuries rather than years. But in the deep ocean, far below the disrupted surface waters, communities of organisms that derive their energy not from sunlight, but from chemical processes in the rock itself, hydrothermal vents and cold seeps, continue undisturbed. Life in the deep ocean continued through the Chicxulub event as it always had, quiet and patient, and entirely indifferent to the catastrophe playing out on the sunlit surface above. Life is, in the deepest and most literal sense, tenacious beyond all reasonable expectation. The recovery. The geological record shows us what recovery from a large impact looks like, and it is, in its own quiet way, one of the most remarkable stories in the history of life. The impact layer at the Cretaceous-Paleogene boundary, that thin band of iridium and soot and shocked quartz that marks the end of the dinosaur age, is followed in the rock above it by a very thin layer sometimes called the fern spike. It represents one of the most distinctive features in the entire geological record, a sudden global abundance of fern spores. Ferns were among the very first plants to recolonize the devastated post-impact landscape. Their spores are extraordinarily resilient, tiny, lightweight, capable of surviving extreme conditions and dispersing across enormous distances on the wind. In the years immediately following the Chicxulub impact, as the fires died down and the soot began to settle, and the first pale filtered light began to return to the surface, ferns were there. Not the lush, diverse fern communities of the pre-impact forests, but a few hardy pioneer species pushing their fronds through the ash, beginning the long, slow work of rebuilding. After the ferns came other plants, more slowly, flowering plants, which had been a relatively minor part of the Cretaceous flora, expanded rapidly into the post-impact world, taking advantage of newly available niches. Trees regrew, but slowly. A forest that takes centuries to mature cannot be replaced overnight, and the earliest post-impact plant communities were dominated by fast-growing, opportunistic species rather than the slow, complex ecosystems of before. And through all of this, in burrows and crevices and the cold depths of the ocean, the survivors waited. And then, cautiously, they began to emerge. The small mammals that had hidden underground during the worst of it. The crocodilians, whose semi-aquatic lifestyle and ability to go long periods without food made them remarkably resilient to the disruptions of the impact winter. Certain species of birds, the only dinosaurs that survived, finding their way through the devastated landscape. Turtles, snakes, the ancient and enduring forms of life that have made it through more than one mass extinction by virtue of their patience and their physiological versatility. Within a few million years, mammals had diversified explosively. The ecological niches emptied by the extinction of the non-avian dinosaurs were, from an evolutionary perspective, an enormous opportunity. The mammals that filled them changed dramatically in that time, growing larger, developing new diets and new behaviors, specializing into forms that had no pre-impact precedent. The horse, the whale, the bat, the primate. All of these lineages trace their origins, directly or indirectly, to the explosive diversification of mammals in the aftermath of the Chicxulub impact. And within 66 million years, a number that sounds large but is, in geological terms, relatively modest, One of those mammalian lineages had developed the cognitive capacity to discover fire, to develop language, to build cities and telescopes and spacecraft, to drill into the rock of the Yucatan Peninsula and retrieve a core sample that contained 66 million years down the thin, dark layer of the impact, and to understand exactly what it meant. That lineage is you, lying here right now, breathing slowly in the dark, your body warm and heavy and at rest. What science is actually doing here is where the story becomes not just fascinating, but genuinely hopeful. We are the first species in Earth's 4.5 billion year history that has developed the capacity to detect an incoming impactor and, in principle, do something about it. The dinosaurs had no warning. They had no telescopes, no orbital mechanics, no spacecraft programs. The asteroid arrived and the world changed, and that was all there was to it. We are different. Not because we are more deserving of survival than the dinosaurs were, but because we are, by some extraordinary stroke of fortune, possessed of exactly the kind of intelligence and curiosity and collaborative capacity that allows us to look outward, to understand the mechanics of the solar system, and to begin, however tentatively, to act on that understanding. The planetary defense community does its work quietly. There are no dramatic headlines most days, no countdown clocks or crisis rooms. Just scientists at their computers, refining orbital calculations, updating databases, exchanging careful notes about the latest observations. The Catalina Sky Survey in Arizona, the Pan-STARRS telescopes in Hawaii, the Spacewatch program, the Atlas Survey, which uses telescopes in Hawaii, South Africa, and Chile to scan the entire visible sky every 2 days. These programs collectively discover dozens of new near-Earth objects every week, cataloguing them, calculating their orbits, determining their hazard status, and adding them to the ever-growing database of known objects. As of the mid-2020s, astronomers have tracked over 30,000 near-Earth asteroids. The vast majority of them, including all of the largest ones, are known to pose no threat to Earth in any foreseeable time frame. The hunt now focuses on the smaller objects in the 100-meter to kilometer range, where the catalogue is less complete. An asteroid in this size range would not cause a global extinction, but it would be capable of devastating a large city or triggering a significant regional tsunami. Finding these objects before they find us is the current primary focus of planetary defense survey work. The DART mission was the proof of concept. A spacecraft roughly the size of a golf cart deliberately crashed into a small asteroid called Dimorphos in September 2022, shortening its orbital period by 32 minutes. The results exceeded expectations significantly, partly because the impact excavated a crater and ejected material from the asteroid's surface, and the momentum of that ejected material provided additional propulsion effect beyond the spacecraft's own momentum. This so-called ejector enhancement means that kinetic impactors are even more effective than theoretical models had predicted, which is good news for planetary defense. Future missions are already being designed. The European Space Agency's HERA mission, which launched in 2024, is traveling to the Dimorphos system to study the aftermath of the DART impact in detail, measuring the crater, studying the asteroid's internal structure, and refining our deflection models. NASA is developing concepts for more capable deflection missions. International agreements for coordinating planetary defense responses are being negotiated and formalized. The infrastructure for protecting Earth from asteroid impacts is being built, quietly and methodically, one mission and one agreement, and one refined orbital calculation at a time. The key in all of these scenarios is time. With enough time, years or ideally decades, even the gentlest nudge applied at the right moment can translate into a miss of millions of kilometers by the time the asteroid crosses Earth's orbit. The physics are deeply forgiving if you start early enough. A change of just a few millimeters per second in an asteroid's velocity, applied a decade before impact, can shift its path by hundreds of thousands of kilometers. The mathematics of orbital mechanics, precise and patient and beautifully exact, are on our side, if we detect the threat early enough to use them. The language of deep time. Let's drift a little now. Let's let the science soften at the edges and become something more philosophical, the way it always does when you follow it far enough. The asteroid belt has been drifting in its slow orbit for about 4.5 billion years. The solar system formed from a collapsing cloud of gas and dust around 5 billion years ago. Before that, the atoms that make up every rock, every ocean, every living thing on Earth were drifting in the interstellar medium, scattered remnants of older stars that lived and died before our sun was born. The universe had already been old for 9 billion years when our sun ignited. 9 billion years of prior history, of stars forming and burning and exploding and scattering their elements across space. All of it preparing the raw materials for this solar system, this planet, this moment. The iron in your blood was forged in the core of a star that exploded billions of years before Earth existed. The calcium in your bones, the oxygen in the air you're breathing right now, all of it was created in stellar furnaces and scattered across space in the death throes of ancient suns. You are, in a very literal and scientifically precise sense, made of stardust. That phrase gets used so often that it's easy to let it pass without really feeling it. But try, for a moment, to actually feel it. The atoms in your body are billions of years old. They have been part of gas clouds, of stars, of asteroids, of ancient oceans and primordial soils, and countless other living things before they found their way, by an unimaginably long and improbable chain of events, into you. The oxygen you just breathed in, that particular molecule right now entering your lungs, may have been part of a dinosaur's last breath, may have drifted in the atmosphere for millions of years after the Chicxulub impact, cycling through the biosphere as life slowly rebuilt itself, may have been locked in ice during a glaciation and released when the climate warmed, may have been exhaled by a tree that stood in a forest that no longer exists, on a continent that has moved since then. It has been everywhere. It has been part of everything. And now, for this moment, it is part of you. Lying there in the dark, breathing quietly. You are the universe observing itself. You are deep time folded into a moment of awareness. The same atoms scattered in the explosion of a star billions of years ago have come together through processes of almost inconceivable complexity and duration to form a mind that can contemplate its own origin. I don't know what to call that other than beautiful. The asteroid as teacher. There's a reason stories about asteroid impacts have captivated the human imagination for as long as we've understood what asteroids are. There's something about the concept that cuts through all the noise and complexity of daily life and asks a very simple, very fundamental question. what matters? When you strip away all the ordinary concerns, the emails, the errands, the quiet anxieties that accumulate like sediment on the floor of your thoughts, and replace them with the vast, patient perspective of geological time, something shifts. The things that felt heavy begin to feel lighter. The things that felt urgent begin to feel optional. And the things that are actually precious, the people you love, the small moments of warmth and beauty and connection that make up a human life, those begin to glow with a clarity they don't always have in ordinary daylight. The dinosaurs had 160 million years. They were not failures. They were one of the most successful groups of animals that has ever lived on this planet. Diverse, adaptable, widespread. Some of them cared for their young with a tenderness that looks, across the vast gulf of evolutionary time, recognizable. They were not simple. They were not failures. They were just unlucky, struck on one particular afternoon by a rock from space that happened to be exactly the wrong size in exactly the wrong place. Modern humans have had something like 300,000 years and recorded civilization perhaps 10,000. In cosmic terms, we've barely arrived. We are in the very early chapters of what Earth life might become. If it survives, if it grows, if it finds ways to spread beyond this single small world. The slow pull of sleep. Every night, without exception, the Earth completes another small arc of its orbit around the Sun. Right now, as you lie still and let the thoughts grow quieter, this planet is moving through space at roughly 30 kilometers per second. That's the speed of Earth's orbit. 30 kilometers every second, day and night, through winter and summer, through every human life that has ever been lived on this surface. You don't feel it. There's no wind, no sensation of movement, but it's happening, always. The planet carrying you through the dark at a speed no human vehicle has ever matched, quiet and smooth and utterly indifferent to whether you're asleep or awake. I find that deeply comforting. The universe doesn't need anything from you tonight. The Earth doesn't need you to stay awake to keep moving. The stars don't require your attention to keep burning. Everything that needs to happen is happening without any effort from you at all. Your only job right now, your one and only task, is to let go. To let the day's thoughts drift to the edges of your awareness and grow still. To let your breathing become a little deeper, a little slower, a little more automatic. You are a passenger on a planet traveling through interstellar space. The journey has been underway for 4.5 billion years. It will continue long after tonight. For now, all you have to do is rest. The ocean of space. Think of space as an ocean. The depths that cannot be sounded. The distances that have no real meaning in human terms. The way it holds everything. Every planet, every star, every cloud of gas and glittering debris. The way an ocean holds its fish and its currents and its floors of ancient sediment. You are, right now, on a small rocky island in that ocean. A beautiful island, improbably alive, with its own weather and its own history, and its own 4.5 billion years of stories written in the stone. The asteroid belt is like the deep ocean floor, vast, mostly silent, mostly dark, home to things that have been there since the beginning and will likely remain long after we are gone. A few of the rocks in that belt have names now. Ceres, the largest, is big enough to be classified as a dwarf planet, almost 1,000 kilometers across, spherical under its own gravity, covered in a layer of ice and ancient dust. Vesta has been visited by a spacecraft. NASA's Dawn mission orbited it for over a year, mapping its surface in detail, finding evidence of ancient volcanic activity. These are not anonymous rocks. They are worlds in their own small way, places with histories. The asteroid belt is a ring of stories. Every rock in it is a piece of the solar system's past, preserved in the cold and dark for billions of years, waiting to be studied by whoever has the patience and the instruments to listen. And we are, slowly and imperfectly, and with tremendous effort, beginning to listen. Returning to stillness. Let's come back now. Let's let the asteroid drift back out to the cold edges of the solar system, far away, unhurried, posing no threat to anyone for millions of years to come. Let's come back to this room, to the sound of your own breathing, to the particular quality of the darkness around you, the way it has its own texture and temperature, the way it's different from every other dark room you've ever been in, because it's yours. The quiet outside your window, or the gentle hum of the city, or the soft sounds of whoever else might be in the house. All of it present, all of it safe. You are here. You are well. You are made of ancient stardust and the residue of long-vanished stars, lying in a small room on a rocky planet orbiting an ordinary sun in one of 200 billion galaxies, scattered across a universe so large and so old and so patient that even the extinction of the dinosaurs barely registers as a footnote in its story. The muscles of your face are relaxing now. The thoughts are becoming slower, softer, less insistent, like leaves settling through water, like starlight arriving after an unimaginably long journey, finally finding a place to rest. The weight of your body against the surface beneath you feels heavier and warmer than it did when you first lay down. Your eyelids, if they haven't already closed on their own, are heavy now. Heavy in the best possible way. The weight of genuine rest, of a body that has done its work and is ready to be still. Let them close. Let the darkness behind them be the same darkness as the room around you, warm and familiar and yours. There is nothing you need to figure out tonight, no problem that requires solving before morning. The thoughts that feel urgent at this hour almost never are. They are just thoughts, moving through your mind the way clouds move through a sky, present and then passing, not requiring anything from you except the patience to let them drift. Let them drift now. Let them go. One last thought before sleep. Somewhere in the solar system right now, this very moment as you're listening, there are spacecraft traveling through interplanetary space. Some of them are visiting asteroids, studying their composition, refining our understanding of how the solar system formed. Some are orbiting planets. Some are drifting far beyond the outer planets, in the deep cold of interstellar space, carrying gold records with music and greetings from Earth, just in case someone or something is ever out there to receive them. Voyager 1, launched in 1977, is now over 23 billion kilometers from the Sun, farther than any human-made object has ever traveled. It passed beyond the heliopause, the boundary where the Sun's influence ends and interstellar space truly begins, over a decade ago, and it is now traveling through the material between the stars, the first human-made object ever to do so. It's still sending signals back. They take over 20 hours to arrive, traveling at the speed of light across a distance so vast that the numbers lose their meaning. scientists still listen. They still care. They still answer. I find that unbelievably moving, that something launched nearly 50 years ago is still out there, still transmitting, still being heard. That there are human beings who sit at receivers and listen for the faint signal coming from beyond the edge of the solar system, and who care deeply about what it says, who have dedicated careers to the study of a spacecraft that will never return, traveling into a darkness that no human eye will ever see directly. There's a kind of love in that, a particular and very human love, the love of knowing, of reaching, of caring about things that are far away and cannot be touched. We are a species that sends love letters into the dark and waits patiently for the reply. That builds instruments to listen for voices we've never heard. That looks at the scars in the rock and asks why. That lies down in the dark and wonders about asteroids and ancient extinctions and what it all might mean. Whatever it means, and maybe it doesn't need to mean anything at all, I think it's enough. I think it's more than enough. And the strangest thing of all is this: the asteroid that struck Earth 66 million years ago, the one that ended the age of the dinosaurs and filled the sky with darkness and changed the course of life on this planet forever. That asteroid made you possible. Without that impact, the mammals would likely have remained small and marginal, living in the shadows of a dinosaur-dominated world. The particular chain of evolutionary events that led to primates, and to human beings, and to the specific arrangement of cells and memories and experiences that makes you who you are. That chain was set in motion, in part, by a rock falling from the sky on an ordinary afternoon 66 million years ago. The catastrophe and the miracle are, in this sense, the same event. The darkness and the dawn are part of the same story. I find that thought worth sitting with, even now, even at the edge of sleep. The things that seem most destructive sometimes carry within them the seeds of something entirely new. The empty niches left by loss become the spaces where new life grows. The darkness, long enough and deep enough, eventually gives way to something it could not have predicted. That is the oldest lesson in the geological record. And it is, I think, a gentle one. Good night. Your body knows what to do now. The slow withdrawal from wakefulness into sleep is one of the oldest behaviors of complex animal life. Every mammal that has ever lived has done what you're doing right now. Every dinosaur before the asteroid came. Every ancient creature that swam in the Cambrian seas 500 million years ago, settling to the sea floor at the end of its day. Sleep is the oldest rhythm, the most universal, the most democratic. It doesn't care how important you are, or how busy, or what you're worried about. It comes for everyone, eventually, patient and unhurried, like a tide coming in across a dark and quiet shore. Let it come now. Let the thoughts about asteroids and extinction events and deep geological time drift away like objects in a slow orbit, present but distant, not gone, just far away, moving in their own patient trajectories, not requiring anything from you right now. The rock is in the asteroid belt where it belongs. The Earth is here as it has been for 4.5 billion years, spinning slowly in the dark. The scientists are at their telescopes. The spacecraft are on their long journeys. Everything is accounted for. Everything is in its place. The ferns are growing back through the ash. The mammals are emerging from their burrows. The slow, patient, unstoppable work of life continues, as it always has, as it always will, in the quiet dark that follows every catastrophe and every ordinary night alike. You have done enough today. You have thought enough, and felt enough, and carried enough. Now you can set it all down. Let it rest on the floor beside you, or drift up toward the ceiling, or dissolve into the dark around you. It doesn't matter. It will all be there tomorrow, unchanged, waiting patiently. Right now, there is only the dark and the quiet and the soft weight of your body and the slow rhythmic rise and fall of your breathing. In and out, in and out, in and out. The Earth turns, the asteroid belt drifts, the stars burn on in their slow, patient billions. And somewhere, in a small room, in a city, somewhere in the world, you are falling asleep under the same sky that has been there since before the first living thing opened its eyes and looked upward. Rest now. You are safe. You are home. You are part of something ancient and enormous and impossibly beautiful. And tonight, all it asks of you is this: to close your eyes and breathe and let the dark be gentle. Thank you for spending this time with me tonight, here on Dreams of Gravity. I hope the journey was a gentle one. I hope the words settled over you like something soft and warm, like the last light of a day that was just long enough, like the quiet that follows the last page of a book you loved, when you close the cover and lie still and let it stay with you a little longer before sleep takes you. Sleep well, wherever you are, whatever time your particular sky is holding tonight. I hope the night is kind to you. I hope your dreams are full of soft light and slow orbits, of ancient rock drifting peacefully in the dark, of deep time and deep rest, of all the quiet things that hold the world together when we close our eyes, of ferns pushing through ash, of mammals stepping out into a new world, of spacecraft crossing the boundary between the known and the unknown, still transmitting, still heard, of you here, now, breathing slowly, falling gently into the oldest and most restful dark. Good night, and thank you for being here.